will use the t-distribution. And this section is going to cover hypothesis testing for the mean with small samples, where we will use the t-distribution. And just to recap what we learned before, the t-distribution with n-1 degrees of freedom as we used for confidence intervals with small samples. Same criteria, n less than 30 or less than or equal to 30. I will never use the number exactly 30 on a test, so that won't be an issue. The population standard deviation is unknown. We only have the sample standard deviation. And of course, the population has to be normally distributed. Now, also, just like for confidence intervals, we're going to get our critical values off of a chart. Because as we learned before, the t-distribution has different shapes based on the degrees of freedom. So we have values that we will use and I'll have to calculate. Now, using the same chart that we use for the confidence intervals, we have, let's see here. Okay, let me zoom in a little bit. Okay. Yeah, we have our confidence levels here on the top row. Now, we have to see how to read this chart with what the one-tail and two-tail means. Now, as we've done with our hypothesis testing, one-tailed actually covers both left-tailed and right-tailed. They both fall under the one-tailed category. Two-tailed, we always know what two-tailed is. Now, the critical values for the z-distribution, these will have the same signs. A left-tailed always had a negative sign. A right-tailed always had a positive sign. And two-tailed always has plus and minus, because it's two ways to reject, two ends. But on our chart, every number is positive, so we have to pay careful attention to what the sign of the value is going to be. All these numbers are positive, so you'll have to realize now when it's a right-tailed problem, you'll look at the critical value alpha in the one tail, and you'll use the number off the chart as is because it'll be positive. If it is left-tailed, you will look up also the one-tail category for the right alpha, but you have to make sure you realize the value will be negative, since obviously the chart won't show that. Now, two-tailed, is the bottom row. Now, two-tailed, we have to remember whatever number we find will always have a plus and minus. In other words, our decision will be to reject if your test statistic is less than the negative or greater than the positive. Now, one thing you have to be real careful of when you're using this, make sure you're on the correct row, because you notice some of these values that are on both rows, but they're in different columns. So we have like a 0.1 in the one-tail second column, but it's in the third column for the two-tail 0.10. Same thing with 0.05 in the third column for one-tail, fourth column for two-tail, and 0.01 fifth column, one tail, sixth column, two tails. So we have to be very careful that we're on the correct row before we scan down there to get our degrees of freedom. All right. So here's some examples I've already done. A left-tailed alpha 0.01 with n equals 7. So if n equals 7, our degrees of freedom will be 6. So left-tailed is a one-tail, 0.01. There I have a column box above the column, 0.01. I would go down to 6 degrees freedom, and right below my box there is the number 3.143. But that's left-tailed, so that means our value will be negative. Pay careful attention. Now the next one is right-tailed, alpha 0.05. And n is 22. So if n is 22, degrees of freedom will be 22 minus 1, which is 21. And now I go to the chart, right tail, that'll be a one tail, but it'll be positive, 0.05 for the one tail, which is the third column. I'll go down here to 22, and right below my box, 21 degrees of freedom, 21 right below my box is 1.721. Because it's right tail, that will be positive. Now, next example is two-tailed alpha's 0.10. N equals 13, so the degrees of freedom will be 12. Now, this will be a plus and minus number. Now, make sure 0.10, two-tailed is the third column. 21 degrees of freedom is 1.721, plus and minus. Also, be careful on this chart not to confuse 0.01 with 0.10. That can be done if you're not careful. All right. Now let's look at how we're going to perform a t-test. The test statistic for the t-test is very similar looking as it was to the z. The only difference is they have s in the denominator as the standard deviation and not sigma. But it's your sample mean minus your hypothesized means divided by s over the square root of n. Now that sentence I have written above the test statistic, the only way we're going to do these, at least for testing purposes, is we will only consider critical values and rejection regions. We will not use p-values. And that is because it's not really practical to calculate p-values. It's too complicated. I mean, yes, the TI calculator will spit them out for us, but since not everyone may have access to that technology, we have to treat this to make it the same for everybody. So we will only use the critical value method. Okay, so let's look at this problem. All right, so computer repair believes the mean repair cost for damaged computers is more than $95. So let's go down here and look at my hypothesis statements. More than is always an alternative hypothesis. That means it would pair up with a null of less than or equal to. Remember, one of our same three pairs that we're working with. And I've labeled that as the claim, which I don't ask you to label the claim on the test. But that would be our hypothesis statements. So let's look at the rest of this. Mean repair cost is 100. Standard deviation's 42.5. At alpha equals 0.01. Do we have enough evidence to support the repairer's claim? Assume the population is normally distributed. That is there to allow us to use the t distribution. It doesn't mean it's a z. It just means we can use the t. Now, supporting the repairer's claim, that's asking, in other words, are we going to reject the null hypothesis? Since the claim is the alternative, that would involve rejecting the null. So let's go to our critical value. And so we have 0.01 with 6 degrees of freedom from our chart. That's a right-tailed test, greater than. So it's automatically going to be positive already. Zoom in a little tighter here. 0.01, let's see. Right there, 0.01, one-tailed. Come down here, there it is right below my box. 3.143. And it's already positive. So since it's a right-tail test, our decision rule will be rejecting to the right. We will reject the null if the test statistic t is greater than 3.143. So all we have to do is calculate the test statistic and decide whether or not it's greater than 3.143. So let's look at the values. I've set up here for the test statistic. It'll be 100, which is the sample mean, minus the 95 for the hypothesized mean, divided by 42.5, divided by square root of 7. Now remember, the degrees of freedom, again, just like for confidence intervals, the formula, you still divide by the square root of n. That's the degrees of freedom is only for looking on the chart. And I get 0.3113, which I put over here in the graph. 0.31 is nowhere close to 3.143, so this is clearly fail to reject. So we do not support the claim that the mean repair cost is more than $95. So here are the calculator boxes here. I think I'll generate this, show you this. All right. Let's see. So we'll go to stat, test, t-test, stats. The hypothesized mean was 95. The sample mean was 100. Standard deviation is 42.5. N is 7. And then we have to choose the alternative hypothesis statement. And it's greater than. Hit calculate. There we have it. There's your test statistic, 0.3113. Yeah, you can see the p-values there, but I will not make, you're not responsible for a test to identify the p-value from a t on a test. You will have to do it for a z, but not for a t-test. But if you just want to look at it because it's there, you can also see that it does validate our fail to reject. Because remember, if the p-value is greater than the alpha, you fail to reject. So we were correct. Okay, let's look at the next problem. AAA claims the mean nightly lodging rate for a family of 4 traveling on vacation in Florida is at least $185. So let's look at my hypothesized statement right down here. At least means greater than or equal to. Greater than or equal to is always a null hypothesis. So it would pair up with less than. So we definitely have a left-tailed test. That's the definition of left-tailed test if you go back to the notes on the introductory hypothesis testing. So let's obtain the sample data results here. 6 families, so N is 6. Mean lodging rate, X bar is 172, standard deviation of 15. Is there enough evidence to reject the claim that alpha equals 0.05? All right, well, let's see. So you see I've identified the sample statistics over here. Now let's get our critical value. So it's alpha's 0.05. It'll be one-tailed with 5 degrees of freedom. And because one-tailed specifically left-tailed, that means we are going to have a negative value. So it's 0.05. Let's see. 5 degrees of freedom. Yes. All right. One tail, 0.05, third column, 2.015. Which left-tailed means it will be negative 2.105. So now you can see my decision rule right here. Reject the null if t is less than negative 2.015. So we calculate the test statistic. X bar is 172 minus 185, the hypothesized mean, divided by 15 standard deviation over the square root of 6. And I get negative 2.123. That's a little close to negative 2.015, but it would be in the shaded rejection region. It is less than it. Pretty close, but it's less than. So we would definitely reject the null hypothesis. I don't have the calculator box for this one, but I'll do it real quick. And okay. So we'll go stat, test, t-test, stats. Let's see. Check the data. $185, 172, standard deviation's 15, and was 6. And this time it's left-tail test because the alternative is less than. We hit calculate. And there you see we have test statistic of negative 2.123. And if you want to glance at the p-value because it's there, you can certainly look at it. And that p-value is a little bit less than alpha, but that also means reject. So we would reject that claim, and we would support the alternative that the Average mean cost is less than $185 for the hotel rooms. Okay. Now let's look at this example. Vicky claims the average GPA for all UHD students is 2.8. All right, is. That's a common phrase for equals. So that means my alternative statement is going to be an equal, not equal. That is a two-tailed test. So let's look at the rest of my data. Sample size N is 22. Mean GPA is 2.65 of that group with a standard deviation of 0.6. At alpha equals 0.05, is there enough evidence to reject Vicky's claim? And looks like it cut off here. So the population is normally distributed. There we go. All right, so let's look at the data. 22. X is 2.65. X bar is 2.65. Standard deviation is 0.6. Alpha is 0.05. So we have 0.05 two-tailed with 21 degrees of freedom. So let's go 0.05 two-tailed. Column 4, two-tailed 0.05. Be careful, we're on the correct row here. 21 degrees of freedom, right below the box, is 2.080. Now, because this is two-tailed, we automatically insert a plus and minus in front of our critical value. So see, the chart only shows a positive number, as you see right here. Plus and minus 2.080 for two-tailed. So our decision rule is to reject the null if t is less than negative 2.080 or t is greater than positive 2.080. So let's look at our test statistic here. So the test statistic is 2.65 minus the hypothesized mean of 2.8 divided by the standard deviation of 0.6 divided by the square root of n, which is 22. And that's calculated out to be negative 1.173, which we can see that's what we have in the box. Now, negative 1.173 is between those two numbers. So, between the two shaded areas, that's your FTR is shorthand for fail to reject on my little graph there. So, that's definitely in the fail to reject zone right there in the middle. So, we would, I made a statement over here to the right saying there is not sufficient evidence to reject the claim of mean UHD GPA is 2.8. Another way when you're testing these test statistics, you can kind of use the absolute value. So in other words, I'm saying less than negative 2.080 or greater than positive 2.080. If you just take the absolute value of the test statistic and see if it's greater than 2.080, that is also another way to do this. So you could sort of say, if I can squeeze this in here, I'm going to say absolute value of t, but I'm going to say it's less than. Less than will be fail to reject. That's another way you can think about it. All right, let's see. So that would conclude that problem. Let's take a look at the next one here. All right, local brewery distributes beer in bottles labeled 12 ounces. Government agency thinks the brewery is cheating its customers with bottles less than 12 ounces. The agency selects 20 of these bottles, measures their contents, and obtains a sample mean of 11.7 ounces with a standard deviation of 0.7. Use a 0.01 level of significance to test the agency's claim. Assume the population is normally distributed. So what do we have here? What's our key statement to identify what our hypothesis pair is going to be here? Less than 12 ounces. So less than, by definition, is always an alternative. In this case, our claim. So it would always pair up with a null of greater than or equal to. So remember, these problems always are going to give you one of the two parts of it necessary to come up with our statement pair. So let's look at our sample. So 20s are in, X bar is 11.7, standard deviation S is 0.7, alpha is 0.01. This is a left tail test because the alternative is less than, so we're going to have a test statistic that's going to be negative. We have to remember to put negative in there. So it's alpha 0.01, and it's 20, so it's 19 degrees of freedom. And I'm not going to go back up with the chart this time, but you would find 2.539 on the chart. Of course, you would have to put the negative in there. So, our statement, our decision, we call the decision rule. The statement right here is called the decision rule. You reject the null if the t is less than negative 2.539. Or if the absolute value of the t is greater than positive 2.539. In fact, let me add that in here. I'll lower my picture. I apologize if that confuses you, me throwing that little bit in there, but this is a way that you can avoid kind of dealing with the negatives. Because sometimes with these negative numbers, especially with decimals, it might be trickier to know which number is larger than the other. So if you kind of make them both positive, then you would know. So look, my test statistic is going to be X bar 11.7 minus 12 divided by 0.7 over the square root of 20, which is negative 1.92. So I have negative 1.92 drawn in there in a graph, if that helps. And it's clearly in the fail to reject zone. It's not to the left of negative 2.539. Or like I said, if you use the absolute value, positive 1.92 is not greater than positive 2.539, as I have kind of put that little statement right there. So we fail to reject. And then we could sort of say then we do not have enough evidence to support the agency's claim that the mean bottle is less than 12.1 ounces. And as most things go in statistics, whether it's confidence intervals or hypothesis testing, the larger the sample size, it always leads to better results. So in other words, if you would have obtained 200 sample size and obtained these same results, there's a good chance that you might have rejected. In fact, I could run that for you real quick in a z-test because it may be more than 30. So, and we'll just look at the p-value. So let's suppose that so we're testing it against 12. Standard deviation is 0.7. N is 11, X bar is 11.7, excuse me. And now I'm just making up an N of 200. And then this is a left tail, excuse me, add extra 0 there. It's a left tail test. And if you look at this, that's, look at that test statistic, negative for Z, negative 6.606, that's way out there. That p-value is super, super tiny. That's just scientific notation. 10, that means it's 9 zeros in front of that 6. So I think that's pretty much clearly less than whatever alpha you would use. In this case, 0.01. So had we obtained 200 sample size, yeah, we would have certainly, and obtained those results with 200 N, certainly would have rejected. But the small samples, it's harder to reject because the sample size can't be as accurate as you can for larger samples. And here's a problem where we're going to calculate, let's see, Yeah, we don't do this for larger samples because it would just be kind of extremely tedious to expect you to calculate the standard deviation. But I believe I did a confidence interval problem like this before in that section. Now, let's see. Glenda claims the average GPA for all students is 2.8. Now, this is similar to the other problem, but now we actually just have the individual data. It's not giving us the mean and standard deviation. We have to calculate it. So here, I won't read out those 8 values, but you can see them in the problem. So those are the sample data that we collected. At alpha equals 0.05, is there enough evidence to reject Glenda's claim? Assume the population is normally distributed. So the only difference between this and the other problem is we have to do a little extra work here to calculate the mean and standard deviation, sample mean. And then once we do that, everything else will be the same. But let's go ahead and let's set up our hypothesis statements. Is 2.8, okay, equal, not equal, straightforward, two-tail. N is 8, so degrees of freedom is 7. And without going actually back up to the chart, well, I think I will for this one. 0.05, 7 degrees of freedom. All right. Two-tail 0.05, 7 degrees of freedom, 2.365. Once again, we have to make sure we're on the correct row, the one-tail and two-tail. So you see I have plus and minus two-tailed 2.365. So here's our decision rule. We would reject the null hypothesis if T is less than negative 2.365 or T is greater than positive 2.365. But as I mentioned right there in parentheses, that's the same thing as just taking the absolute value of your T, so essentially just making it positive if it's negative and seeing if it's greater than 2.365. So here, okay, sample mean, that's easy enough to do. Add them up, divide by 8, it's 2.9. And I showed both formulas for calculating standard deviation. Of course, if you're just using the TI calculator, you would just do this whole thing as a t-test. You wouldn't have to go through all this. But it looks like I went ahead and used the original formula instead of the shortcut formula. I know most of the time I tend to advise using the shortcut formula. Most of the time I like it, but sometimes like this, since the mean didn't have a bunch of decimal places, like if it had been 2.9235 or something like that, I don't think I would have done all those subtractions this way. But since it was just 2.9, I kind of went through it and just did it using the formula up here on the left, this one. But for the most part, I still advocate using the shortcut formula, which would have been fine if you would have done that. So the sum of x minus x bar squared all adds up to 0.68. So this is a sample standard deviation, so we divide by n minus 1. So it's the square root of 0.68 divided by 7, which ends up being 0.3117, which I come over here for my test statistic, and there's what I use in my denominator, 3117. So it's x bar 2.9 minus hypothesized mean of 2.8 over 0.3117 divided by square root of 8. That is 0.89. So I drew a little picture here. 0.89 is clearly between those two regions, so we would fail to reject. And we could say there is not sufficient evidence to reject the claim that the mean GPA is 2.8. So here is the result. If you just would have. So what, as I'm mentioning over here, kind of going back to what we learned earlier as far as using the calculator, you would go to stat, edit, list, and then enter your values all on the list, and then you can quit out of that. You don't do the stat calc. You can just let the t-test take care of everything. But so we would quit out of that. Then you'd go to data this time instead of stat. So data means when you have your values in a list, 2.8 is your hypothesized mean. So now the list is telling you that we're telling it the data is an L1. That frequency number, I don't know what it means, but it has to be 1, so there's no reason to ever change it, and it's always defaulted at 1. Our alternative is not equal. Hit calculate, come over here. And you can see it showed us our mean down there, 2.9, showed us 0.3117, so it looked like we did that correctly. And then up here, our test statistic, 0.91, and I got 0.89 doing it that way. Just a slight rounding error, but not enough to, I'll certainly be aware of that for exam purposes to make sure that something doesn't end up where it's too close, as far as making a rejection decision. The main difference in this calculation, though, is that they are, that calculation is using the standard deviation. You see from the calculator, it has all those decimal places instead of just rounding it off. So you can see that's why it's important still, though, if you would have calculated standard deviation, to use about 4 decimal places or so your answer doesn't get too far off. Here it's only a little off, but not enough to affect anything. And that concludes this section on hypothesis testing for the mean small samples.